I think I'm the last presenter, so I'll try to go through the process and explain. This is a research project that we've been working with Pontifical Catholic University of Rio de Janeiro with my colleague Flavio Silva and his team. And the idea here is to run fatigue tests, but try to develop a model that would allow you to characterize not only fatigue performance of concrete in a flexural mode, but also do it on a reinforced concrete. What is the fatigue performance of a reinforced concrete that has fibers in there, and it receives contributions from basically both the steel rebar as well as the concrete phase. Now, recently I was in Germany, and I had a chance to just go for a visit of this bridge that collapsed in Dresden. The bridge collapsed at midnight without any traffic on it, and the problem was attributed to stray current corrosion, not stray current corrosion, but primarily just the fact that it was built in 1970s, early 70s, in East Germany. It was post-tensioned, and there was absolutely no way to tell from the surface of the bridge that there was corrosion. So this is the corrosion of the pre-stressing tendon. But the fact is that it was being used for more than 40 years or so, and there was no redundancy in the system to distribute the load. There were large sections of the concrete that were connected without any reinforcement, because they were depending completely, in the negative moment region, they were depending on the post-tensioning region. But the report is going to come out soon. And what we are concerned in is the fact that we're designing enormous structures which fatigue becomes a major component of design of the foundation. 40% of the cost of a wind tower primarily is spent in the design of the foundation and its construction. So these areas are going to become extremely relevant. The cost of using rebar is going to be extremely high to put those systems together. And what we need to consider is that how can we use fibers as a means of improving the fatigue resistance? So this is a project that we are involved in, but within this project, I'm only primarily interested in the modeling part, simply because of the fact, as much as I love to be spending a lot of time in Rio de Janeiro, but we have to stay in our university and do the work. So we do flexural tests, as I've talked about in the previous presentation, uniaxial pull-out test, because the bond is important, dynamic analysis and damage identification to simulate the response, reinforced concrete in tension, modeling of the flexure, and also the modeling of the pull-out of the rebar. That one area that we published in this area is fibers by themselves improve the bond characteristics and bond capacity of the rebar significantly. So at every stage of this process, until we get to the final reinforced concrete subjected to fatigue, there is something to be learned at every interaction that exists. So here's the mix design. The parts that I want to emphasize is that it's the rather high performance concrete with about the amount of cement about 360 kilos per cubic meter, and the steel fibers were Beckart, Dremix 3D 4530, crimped end, and the study looked at 20 kilos, 40 kilos, and 60 kilos of steel fibers for a matrix that's 50 megapascal compressive strength. Now, the way the test is done is that we have to start with a pre-cracked specimen. So you can, of course, start at this level and go through maybe about a very low level of loading, and like previous two speakers, just initiate the crack. So the initiation of the crack would basically do what we do in terms of the pre-cracking specimen and unloading. So the criteria here in these experiments was load it up to 0.5 millimeter crack opening. At that point you unload and you go through the cycles of the fatigue test, or to the end of the test. End of the test was defined as 1 million cycles. So for every specimen was intended to go through this level of the testing until it failed at different levels of the fatigue load that were applied. Now, the load level was, different load levels were used, but then, for example, what we say is that P up of the, the upper bound of the unloading was defined on the main curve, so without unloading completely. So at the CMOD of 0.55, it can be FR1 value that was designated as upper load, and then we went at 50% or other. One can run it at other levels of it, other fractions of the load to define the R value for the test. CMOD was monitored by clip gauge throughout the entire test because that is the most important parameter to measure, and then try to characterize the mechanical response. Now, the response that we calculated was based on the assumption of the a two-parameter type of a Weibull distribution, which if you assume that your strength is basically by the two parameters of U and alpha, then when you plot it on a log scale, then you would get a linearized curve. So two-parameter Weibull would give us a linear curve, and a three-parameter Weibull gives you a slightly better curve fit, but then now you have a nonlinear type of a curve. Going to up to 1 million cycles, the tests were run at different levels, 90%, 80%, and 70% of the value of the upper limit to calculate for to generate the SN curve. So these are the basic SN curves of the samples. And one can, based on that, develop failure probability, 50%, 5%, 50%, and 95%. So this can be used from an engineering point of view, a good way to design based on the level of the load with respect to FR1. So you only need the FR1, you need the SN curve. Based on this, you could basically design it with a good degree of probability that the sample is going to be safe in these designs. Now, one other way that we can also look at the data is what we've done on the full-scale structures, is to focus on the stiffness. So as you're going through these cycles, million cycles, you can look at a few cycles and look at the hysteresis response, define a stiffness parameter. So the stiffness is basically the slope of one cycle as it goes up and down. It's an elastic equivalent response that we will get. And so this is Kn over N. So basically, this K stands for the stiffness, N is the cycle number, N is the total cycle number. So this is your cycle ratio, which would basically show up on the plot, and we can monitor the rate of degradation of the stiffness of the sample. You can count, given a value of the cycles of load and the level of the steel fiber content, 20 kilos, 40 kilos, and 60 kilos, one can actually calculate what kind of a stiffness can I expect to get. This stiffness only is about your fatigue response. So you can check it for the design, or see if the value is low, or if there is a sudden, let's say example is you load it for this many cycles, and then all of a sudden you change the rate. You would do some kind of a hybrid type of a loading where you first load it to a certain level of stress, and then all of a sudden you have an overload, 5 cycles of overload to, let's say, 150% of this upper limit that you emphasize. So the stiffness can be used to actually see whether we can jump from one curve to the other curves. Now, the same approach can be used to calculate from the stiffness, normalize all the curves with respect to the maximum level, and define a damage ratio, which basically says that for a given value of the cycles that we're going through, what is the overall stiffness reduction of the specimen? Calculating, again, some type of a probability distribution of the stiffness of the sample. Of course, the next step is to go through a full-scale test. I mean, it's a small model test, but now you have a rebar in the middle 4-point bending zone. We have no shear reinforcement provided, so that the probability of the failure of the sample in the linear moment region of the beam is very small. So now we can focus on this area, start doing few cycles to get ourselves to a pre-crack zone. Once it's cracked, At that point, you just go up to a certain finished level of the slightly above the FR1 value. So we just basically skip the test, go to the FR1 value. At that point, you unload, and now the green curve shows the creep process, the fatigue process that we go through with a sinusoidal function. So these are very good ways to look at it, and you can define it by any stress. So this is the part that these experiments become extremely tedious, because you can run this test, the ratio of the minimum stress to maximum stress as 0.3, with the maximum stress being at the level of the FR1 level. The way we look at the FR1 is that we don't want to use it as a stress design parameter, but as a way to control each specimen independent of each other that we have. So these are some of the data, really interesting to take a look at them. When you're going with at 80% of the load range, now basically what we do is we load the sample to the level of the cracking. This is for the reinforced concrete beam before we've gone to the higher level, and then we go through the cycles. We can go to up to about 580,000 cycles on this particular sample of the reinforced concrete beam. This is plain concrete, which means that after the cracking of the concrete, basically now what you're doing is primarily you're doing the steel. The steel rebar is the one that's carrying all of the force and resisting the fatigue. So it is the steel strain that's measured in this range. If you go with a reinforced, steel fiber reinforced concrete and use that same level of the stress that was used for the FR1 value of the sample, now what we do is we go to this same level of the stress and we run our fatigue tests. Now we go 1,000 times, 5E6, 5 million cycles we can go actually without much loss of stiffness, because with the rebar, now you don't even get the rebar to go to any kind of a yielding or accumulation of the yielding. That's what's so important about using steel fibers that I've been pushing so much, that the fact that we use fibers, it reduces the stress on the steel rebar, which means that in the serviceability range, steel doesn't feel a thing. It's elastic. So the definition of elastic is it returns always back to the state of zero stress, doesn't feel a thing. And that's basically the key point that we can emphasize from here. And it can, so it reaches, but then ultimately there is life to everything. And so one can reach that yielding after, what's the number? Yeah, 5 million cycles. So you have to load it at this stress to 5 million cycles to yield the rebar. You can also, now another way of doing it is to say, what if our load that's being applied is 80% of, at what point do we reach the 80% of the rebar yielding? So I want to stop the test before the rebar starts yielding, and that would be at the, at around 488,000 cycles. So again, the key point here is to show that even when we go with 80% of the FR1 value for concrete, your steel is going to be carrying a significant amount of, is going to contribute, so the contribution of the steel comes in afterwards. This is another way of looking at the data. When does the steel start going yielding? And that can be calculated from a comparison of the two curves. Nearly 30% increase in the capacity. At 5%, if your load is at 5%, then you go to a runout, which means that it indefinitely goes. How do we model it? I do not believe that we can use FR1 or FR3 in any shape or form in the design process unless we scale those parameters. The only way to do it, in my opinion, is to get the data and come up with the tensile stress-strain response, add it to the steel rebar, and generate a model based on strain compatibility analysis. If we don't do strain compatibility analysis and just simply add different contributions from fibers and concrete, that's a slippery slope, in my opinion. We need to do the strain compatibility analysis to add everything on the strain profile that we get. So if fatigue causes increase in the strain, what we can do is to implement that strain on top of a strain compatibility, recalculate our stresses, and based on the stresses at critical points that we define, we call it control points, calculate the moment curvature. All of the modeling can be done at the level of the moment curvature. And that's, again, another issue that I'm pushing to say that the curvature at the end is the curvature that's accumulated because of the creep plus the curvature that was applied by the load on one structural section. So there is no double counting. And the best way of doing it is to probably now for this type of a model is to obtain an SN curve for the steel rebar. And from that, you can add it to this restraint curve that we have. Calculate from that stress, calculate the effective strain due to the fatigue, and this strain is added to the initial strain, which would be the load that's applied. This function gives us a moment curvature, and with the moment curvature response, which is basically a summation of these, we can actually calculate what's the residual capacity of the overall structure. So that would allow us to basically take a look at, start with the steel rebar stress range, the stresses that the steel rebar experiences. Note that there is no fatigue curve for the steel rebar if you're in the elastic range, as long as you're in the 10% or 20% in the serviceability level. So with this curve, and then the material model is the tension model for plain concrete, tension model for steel fiber reinforced concrete, which the difference between these two is only in the post-cracking range. This is the strain that's hidden, and it's represented by FR1 or FR3, but it's not directly associated with them. And then the steel rebar model, that if we stay in this elastic response, we keep going up and down for millions of cycles. Now we are able to run the experiments and use this back calculation approach to actually see how does the structure behave if we start with a reinforced SFRC beam. The model and the experimental data is shown. We have very good fit. If we go with the RC beam, the same set of parameters. Again, now here, all we have is depending on the load distribution. Since the steel is the only component that's carrying the load, now this moment or this force, about 20 kilonewtons, 25 kilonewton, is dumped on the steel, and now the fatigue response of the steel kicks into the effect. We can also compare it, so this is a force deflection. From that, we also base it, but this force deflection wasn't calculated up in the air. It was calculated based on generating the moment curvature, and we see that if we simulate the moment curvature, we can go back and give the designers a very reliable value on how much load the section can take. At this point, then basically the case converts into coming up with a master curve that can be an average of all of the values that we are using in terms of the value as a function of the stress ratio. And for different stress ratios, we get a master curve for the strain in the steel as a function of the number of cycles. And using that, this curve is what is used to generate for different stress levels. We would be able to develop the strains, and the strains are used in order to simulate the response of the section depending on the creep level. Of course, the model would allow us to load it, unload it, and then load it again. So this is, again, another way to look at the steel strain as an indicator. It's like the canary in the coal mine that tells us the strain of the steel represents how much load is being carried by concrete phase, or whether the steel is on the verge of failure when we're talking about a real structural system, such as a reinforced concrete beam. And it also, now once you go to a hybrid system, then it becomes generating the response, what's the contribution of the fibers in the case of a machine foundation, for example. In my opinion, design of machine foundations would really benefit from this type of a model, because we can actually predict the response of how much bending moment we can carry for a given set of fatigue response, the amount of the steel fibers, the amount of steel rebars from a hybrid design point of view. And it all goes back into coming up with the master curves that generates using these curves, we generate the curvature on the cross section as a function of the number of cycles. Reinforced concrete, initially this way, but then with the experimental, once you collect the initial cracking and then the follow-up for the characteristic definition. So we see the ductility, curvature ductility that the fibers also bring. So this type of work helps us not only from a design point of view, but also from a better understanding without any variable. We can do it for other types of fibers. It's not really specific to the steel fiber, but it is just a very positive way, in my opinion, to showcase that the best place to use fibers is for serviceability-based design, getting away from ultimate strength, because you can do that with our standard traditional methodologies. Thank you so much for your attention. I think we are pretty much done. And this is just basically some videos showing how, these million cycle fatigues. And this is the part that's measurement of the crack width and the oscillations of the crack width as a function of the length. Thank you so much.